Hello and welcome to another Java tutorial. In this tutorial, I'm going to look at the general Runge-Kutta family methods for solving ordinary differential equations, either a single equation or a system of ordinary differential equations. And we already looked at the Euler method, midpoint method, and then the Runge-Kutta fourth order, and we mentioned that Euler method and the midpoint method are actually in fact part of the Runge-Kutta family. But what is the general Runge-Kutta family? So the general Runge-Kutta family, again, the idea is the same. It creates an iteration or a sequence of y values, the solution values for the solution, and these solutions can be either a single function if we are solving one single ODE, or a vector, okay? And could be a vector of solutions, n solutions, which are the solutions of n system of ordinary differential equations. So in general, we end up with an iteration, yn plus 1. At the n plus 1 step is yn plus something. And obviously, h is the step size. And again, we mentioned that we always, for solving ordinary differential equations, we always use uniform steps or uniform partitioning. So I'm going to write it again here, because it's just simpler and partitioning. It's just easier to deal with compared to the quadrature methods or nonlinear step sizes. So h here can be considered a uniform step size, and then so in the nth step of the solution, in this sequence that converges to the value of the solution of the ODE at a given point, then at x, for example. Again, let's go back and just quickly look at the approach here. So the approach is that if the initial condition is given at x0, which is equal to a, y0 is given, which is y of a, and we want to find the value of the solution y at some later point b, we basically partition the interval between a to b into n sub-intervals, and the length of each sub-interval is h, which is a uniform partitioning, so all the sub-intervals have the same length. And we said that we create a sequence yn, right? y0, y1, y2. From y0 we find y1, and then y2 all the way to yn. And we said that this sequence, as we increase the number of sub-intervals, the accuracy becomes better and better. So this sequence yn, as n goes to infinity, it does in fact converge to the value of the y, the solution at the point b. And then we said that if we want to find the solution at many x points, we just do this for every single point, right? Now, we said that this sequence can have an order of error, right? So we saw that this yn, the way we create this iteration, yn plus y equals 1, so this can give us an error between y of b, for example, the value of the solution, the exact value, and the numerical solution, yn, the iteration. And we said that for Euler it's order 1, order h. For midpoint, it's order h squared. For Runge-Kutta fourth order, we saw that it was order h to the fourth power, right? And then, so in general, there's the Runge-Kutta family has this format. So there are a few things. One is this s parameter. So we already know what h is. H is the uniform step size. Yn is the value of the iteration, right? y0, y1, these are the sequence that we calculate starting from y0. So we need to know s. S is called the number of stages, right? It's an integer, positive integer. It's called, and it starts from 1. So 1, 2, 3, etc. S is called the number of stages. B and K, Bi and Ki. So we need these three factors, S, Bi, and Ki. So Bi is just some numbers, right, that are given. For example, for midpoint, it was 1/2, right? For Runge-Kutta, it was 1/6. 1 over 3, 1 over 3, 1 over 6, something like that. And then ki depends on how many stages we have. For example, k1 is always f of x and yn. So if I'm at step n and I want to calculate step n plus 1, k1 is always f of xn plus and yn. k2 end up with we have another sequence of coefficients, which is c, c1, c2, c3, all the way cs, if we have s stages. And another matrix of coefficients aij, right? So we need to know s, we need to know aij, because ki's are determined based on the c and a. So we need to know aij, bi, these coefficients, to be able to do this summation. And then in order to find ki, we need to know ci, this c coefficient, and this matrix coefficients aij, right? aij, bi, and ci. We need them. So s, the number of stages. In general, s gives us the order of magnitude for the error, right? aij, bi, and ci are specific to a particular s. And the way we sum these up in a very nice visual way is called basically the Butcher Tableau, right? The coefficients for any Runge-Kutta method, any family of the Runge-Kutta method, is summarized in the Butcher Tableau. And the Butcher Tableau is in something like this. So we have this half matrix, right? A11, so it has s rows because we have s stages. And then bi's are given at the end, right? b1, b2, bs, and bs minus 1, and bs. These are these coefficients that we know and we need them. And then in order to find ki's, each ki corresponds to the ith row here, right? In order to find ki, we need to know ci and then the aij's for that particular ki, all right? For example, basically here c1 is always 0, a11 is always 0, so k1 is f of xn and yn, right? And for a particular row ki, ci, these c coefficients are for incrementing the x, so xn plus ci times h, all right? So this and the aij coefficients are for incrementing the yn, all right? So the yn plus h times aij times ki. So it's kind of like a recursive way. In order to calculate k2, we already need to calculate k1 first, all right? In order to calculate k3, we need to calculate k1 and k2 first. So let's just have a quick look at the first few rows. c1 is 0, a11 is 0, so k1 is f of xn plus c1 times h, which is 0, so it's just xn, and yn plus a11 times k0. There is no k0, and a11 is also 0, so k1 is always f of x and yn, all right? And then k2 is f of xn plus c2 times h, this row, and yn, so the increment of yn is yn plus h times a21 times k1. So the increment of y is h times a21 times k1. K3 is basically f of xn plus c3 times h, and then increment of yn, so it's yn plus h times a31 k1, a32 k2, okay, and all the way to the end, cs. Ks is f of xn plus ch times h. This is the increment. H times this coefficient is the increment of xn, and these coefficients times k1, k2, etc. times h are the increment of y, all right? So there are two very important things for a general Runge-Kutta family in the Butcher Tableau. The first one is the consistency condition. That means that the summation of the aij coefficients at each row must be equal to the c in that row. That's one of the main conditions. So we see that a11 is c1, yes. A21 is equal to c2, it's always the case. A31 plus A32 must be C3 all the way, etc. All right? And we always need the B1, B2 all the way to BS. But then the other one is the order of error. If order of the error for a S stage Runge-Kutta method is order of h to the p power, all right? Then this table tells us what is the theoretical minimum for S that we need to achieve that order of error for the numerical integration, all right? So the most important thing here is that if I want to have order of 1, 2, 3, 4, theoretically I only need 1, 2, 3, and 4 stages. So the minimum number of stages is equal to the order of the error that I'm looking for. However, after 4, something very interesting happens, that if I want to have order of h to the 5th power, I cannot have 5 stages. I need to at least have 6 stages. And that's very clear here. So for order of h to the 6th, we have 7 stages, and etc. For 8th order, order of h to the 8th power, we need 11 stages. That's why I mentioned before that the 4th order Runge-Kutta is like the sweet spot. Why? Because after that we need to have 6 evaluation of the functions, and then it just grows rapidly. So it may not be computationally interesting, and the 4th order Runge-Kutta is kind of like the sweet spot, and it always, in most cases, it gives us good accuracy with good speed, because we only need to evaluate the function 4 times, right, and get a 4th order error. Now we have already looked at the midpoint. So Euler is a stage, 1 stage, right? Everything is 0 here, and C1 is 0. So Euler is yn plus 1 is yn plus h times b1 times k1. b1 is 1 and k1 is f of xn and yn. So Euler is the simplest one, and obviously you can see here that with 1 stage we get an order of 1, with 2 stages, which is the midpoint, we get order h2, h to the 2nd power, etc. So I have here a few examples. Midpoint, it has 2 stages. Theoretically it can give us order of h to the 2, 2nd order error, and the Butcher Tableau is this. So the first row, we need 2 k values, k1, k2, yn plus 1 is yn plus h times b1, k1, b2, k2, and b1 is 0. So it's only 1 times k2, b2 times k2, all right, that's the iteration. And in order to calculate k2, we need to calculate k1. So k1 is always, so the increment of xn is 0 because c1 is 0. The increment of yn is also 0 because a1, 1 is 0. And people usually don't write a1, 1. But so k1 is always f of xn and yn. And then k2 is f of xn plus the increment of xn, which is c2, 1/2 times h. And yn plus the increment of yn, which is h times a12 or a21, which is 1/2 times k1. And this is exactly what we looked at when we talked about the midpoint method, all right? So k2, so yn plus 1 is yn plus h times f of xn plus 0.5 h, yn plus 0.5 h k1, which is f of x and yn, all right? And this gives us order h squared. 4th order Runge-Kutta, it has 4 stages, and in theory it's the minimum stages that we need, or we can have minimum stages that we can have to end up with a 4th order error, right? So this is the Butcher Tableau. We have 4 rows, C0, C1, C2, C3, C4, and these are the A coefficients and these are the B coefficients. And the iteration sequence is yn plus h times sum of bi times ki. H times b1 is 1/6 times k1, b2 is 1/3 times k2, b3 is 1/3 times k3, and b4 1/6 times k4. This is our iteration, and we construct the ki's based on each row of this tableau. So K1 is always the first row, which is f of x and yn, always. K2, we calculate the increment of xn, and then we calculate the increment of yn based on the aij. So increment of xn is c2 times h, which is 1/2 times h. The increment of yn is h times a21 times k1, so 1/2 k1. So k2 is yn plus h times 0.5 k1. All right. K3 is xn plus 0.5, which is 1/2 times h. That's the increment of xn. And for increment of yn, we end up with h times 0 times k1, 1/2 times k2. And for k4, we have increment of xn is 1 times h. Increment of yn is 0 k1, 0 k2, 1 k3. So this is exactly the Runge-Kutta method. Let's go back and look at it from before. Euler method, midpoint method. Let's see, where was the Runge-Kutta? Midpoint, Runge-Kutta. This one. H times, here I defined K1 including H, but in the general Runge-Kutta and the Butcher Tableau, H is always outside, all right? So it's better to consider H outside here. And we said that it's 1/6 times f of x and yn, and all the way. Now you can in fact include h in the Butcher Tableau. Basically, you have to always keep in mind that the increments of xn and yn are basically these coefficients times h. H multiplies by all these coefficients, and these k1s multiplied by h. So you can in fact define h inside of each one of these k1, k2, k3, k4, etc. But it's customary not to do that. H always is outside, right? And now there are two other methods that I mentioned in the beginning of this chapter, but I never went into the details of them. So here we can easily look at them. One is the Cash-Karp method that has 6 stages, and it has an extended Butcher Tableau. So the extended Butcher Tableau means for BIs, we have 2 rows. All right. So the AIs and AIJs and CIs are the same, but we end up with 2 rows for BIs, and one of the rows of the BIs gives us a 5th order error, and the other row gives us a 4th order error. Here the first row gives us a 5th order error, and the second row gives us a 4th order error. And this is a very good thing to have, because then we can calculate the solution with the 5th order error, the first row, and then also calculate the solution again with the 4th order error, and know that in order to do these 2 calculations, we only need to calculate the KIs 1 time, right? Because everything is the same for KIs. Only BIs are different. So we can easily get a 4th order and the 5th order errors simultaneously, but we can then use that as a comparison. So the difference between the 4th order and the 5th order error gives us a sense of how much the error is, the general error, right? And based on that, we can actually adjust the step size. So h doesn't have to be the same as we progress from x0, from a to b to c to d, etc., right? As we progress for the solution in the x-axis, we don't need to, and that's the basic idea for adaptive step sizes. All right. So Cash-Karp method, and the other one is Fehlberg. Again, it also has 6 stages, and sometimes it's also known as Runge-Kutta Fehlberg 4-5. RK 4-5 is basically the Fehlberg with 6 stages. It's different from the 4th order Runge-Kutta. So when we say 4-5, it means it can give us both a 4th order error and a 5th order error, and that's typically what is being used for adaptive step size solutions, adaptive step size algorithms. All right. And here's the Butcher Tableau. Again, the first row gives us the 5th order error, the second row gives us the 4th order error, and once again, the implementation in our Java code is exactly the same as before. We first create a sequence, Fehlberg sequence that converges to the value of the solution at x1, for example, starting from the initial point. And then the only thing that changes is this for loop that generates the iteration, right? yn sequence. And we implemented this for Euler, Midpoint, Runge-Kutta. Now we're implementing it for Fehlberg, all right? And everything else remains the same. So this for loop, this is a multi-line lambda expression that creates yn, and this for loop basically uses a uniform partitioning for x and then an iteration for y. So yn plus 1 is yn plus, and I'm implementing the fifth order Fehlberg method, y plus h times b1 k1 b2 k2 b3 k3 b4 k4 b5 k5 b6 k6. all right, so b1 is for fifth order is 16 over 135. Just make sure that you use the double numbers, not the integers, because if you just write 16 over 135, Java compiler by default assumes that you're dividing integer by integer, so it doesn't give you the exact double value, and that causes pretty much this Fehlberg to fail. all right, make sure you convert this to double. At least one of them should be double so that the end result is also double. So I'm writing k2 multiplied by 0, but you don't need to write it in general because b2 is 0, and then 6656 over 12825 times k3, etc. all right, so I have k1 k2 k3 k4 k5 k6, and in each step I calculate all these 6 as xn and yn, and then we go to the next xn plus 1 yn plus 1, etc. So k1 is always f xn yn. K2 is the increment of xn is 1 over 4 times h, so x plus 1 over 4 times h. The increment of yn is 1 over h times 1 over 4 times k1, y plus h times 1 over 4 times k1. For k3, the increment of xn is 3 over 8 times h, so x plus 3 over 8 times h, and then the increment of y is h times 3 over 32, h times 3 over 32 times k1 plus 9 over 32 times k2. And again, I'm converting all of these to double to make sure that the division is correct. all right, so etc. For example, in the last row, the increment of x is 1 over 2 times h, and the increment of y is h times minus 8 over 27 times k1, 2 times k2 minus 3544 divided by 2565 k3, etc. all right, and that's the implementation of the Fehlberg. And once we have this sequence, the rest is exactly like before. So let's head to Eclipse. In my ODE, in the ODE solver, now I have this Fehlberg sequence. I have both fourth order and fifth order, and here I'm using fifth order, so the fourth order is commented out. all right, and once we have this sequence, we can calculate the value of the Fehlberg, the solution, by getting the sequence and evaluating at after 10 iterations in the sequence, right? The 10th term of the sequence. all right, just like Runge-Kutta. For Runge-Kutta, we also use the 10th term, 10th step, or anything after that is probably fine. And then if you want to get a solution for an array of x values, we call the Fehlberg, we update the initial condition, and each step we use the previous solution, previous step as the initial condition. That's why our accumulated error remains very small, right? And this is a very standard thing. The only thing that we change the name of the sequence and the Fehlberg. And if you look at, for example, Runge-Kutta, as soon as we implement the sequence for that method, evaluate at 20, and let's also evaluate this, for example, at 20, and again, Runge-Kutta use the sequence value at 20, and then for an array of x values, everything is, the code is exactly the same. We just change the name of the method here. All right. And then in the test package, I have the test Fehlberg. So here I'm solving basically y prime equals y squared with y0 equals 1. So derive function, because this is one ODE, I call the derive function x and y, returns minus y squared. The initial condition for x is 0. The initial condition for y is 1. I create an ODE solver, and if you recall, I defined this ODE object before. It has only a static method. Basically, it's a helper class, and what the helper class does, it has private constructors, so the user cannot instantiate it. But it has one method that has been overloaded, get solver, all right, and it's going to help basically it's going to help the user to select the correct ODE solver object. So based on what derive function the user passes in and what initial conditions. So the user doesn't know which solvers we have. The only thing that the user needs to know is what kind of derive function to define. So derive function means a single real valued ODE, and once we call the ODE.getSolver and pass in this function, it already returns the correct value. So it returns an object ODE solver, the correct solver, right? And then I want to find the solution from x0 to x0 plus 50 for 1000 points with these initial conditions, and I'm going to use compare four methods: Fehlberg, Runge-Kutta, Euler, Midpoint. So blue is the Fehlberg, red is the Runge-Kutta, green is the Euler, and then the black is Midpoint. So let's run this. As you can see, we pretty much have the same solutions. So all of them seem to have enough accuracy. Let's see if we can differentiate them. Yeah, we're starting to see something. So green is Euler, so it has the least accuracy, and then the black is Midpoint. Blue and red are Fehlberg and Runge-Kutta. They pretty much have the same accuracy. You see there's a little bit of difference. It's extremely small. So yeah, both Runge-Kutta and Fehlberg give good results here. And Fehlberg gives us a 5th order error. Runge-Kutta 4th order gives us a 4th order error. And all of them are pretty fast, all right? So that's how we implement Fehlberg. Again, if I want to use the Fehlberg now in the ODE system solver, for example, everything else is the same. So for example, here we have the array sequence for Runge-Kutta. What I'm going to do is do exactly the same thing for Fehlberg, all right? And all we need to do, we need to just change this. So from ODE solver, I get the Fehlberg sequence, and then let's copy this. So we have to have ND arrays K4, K5, and K6, all right? And basically, let's see. Let's copy all of these here. Let's remove this 4th order one. And then K1 becomes basically func.values. And we're going to remove the h here and put the h here, h times K1, all right? And then value y.array, right? So this is our K1, and then K2, we're going to remove this, and k2 becomes values. The increment of x is correct. The increment of y is y dot so y plus this, all of this becomes an ND. So y is an ND object, ND array object. K1 is also an ND array object. The operators are already overloaded, and we have to call the basically let's see. So I feel like there is an extra parenthesis here. No, okay, so what we want here is this one that encloses this and call the array. Okay, so this is k2. X is real number, so this function is basically deriv n function. So k2 is also done, and then k3, the same thing here. Let's do this, k3, and also ND array, k4, k5, k6, 5, 6. All right, and then y is this iteration basically. All right, operators are overloaded, so we are good. We're implementing the fifth order, and then k2, k3 is this func, and the values, we take the y plus whatever that is here, we put this one here, dot array. All right, so k3 is okay now. K4 is this line thing, and we put it here for k4, func dot values, and basically we are going to add another, let's see, so it's this one, dot array. This is k4, so k4 is gone now. Let's go full screen here. So k4 is gone, and now k5, func dot values, y. Okay, so we do this, dot array. So k5 is good now, and finally k6, values, we end up with this, and then this, and get the array representation. All right, and again, we're doing all this ND array to not go into the a lot of for loops here, because now ND arrays, the operators are overloaded. It makes us create a very nice looking code. All right, but once we have this Fehlberg sequence, everything is exactly the same. So if I want to calculate the solution at some number, at some x, using the Fehlberg, I call the Fehlberg sequence, all right, and then evaluate it at 20 terms, at 20 steps, and then the array. And if I want to find the solution at an array of x values, I again have Fehlberg. Everything is the same here, I just call Fehlberg. All right, everything is exactly the same, and that's how easy it is to solve. And then we can also implement Cash-Karp. It doesn't really matter that much. It's eventually up to you. Every ODE solver method has its own advantages, because again, solving ODEs also depends on the ODE itself, the behavior of it, the stability of the ODE, and other things that we have to consider. So there is no one method for solving all the different types of ODEs, right? But typically fourth order Runge-Kutta is the normal thing to do, right? So this was basically the general idea of the Runge-Kutta family methods, and I hope you enjoyed this lecture, and I'll see you in the next one.